Welcome. In this video lecture, we're going to cover the first part of section 1.1, the geometry and algebra of vectors. Now, I've divided this section up into 5 different parts: vectors in the plane, new vectors from old, vectors in R3 and Rn, and I'll cover those 3 topics in the first video lecture here. And then we'll take up linear combinations and coordinates and binary vectors and modular arithmetic in a second video lecture on section 1.1. So let's begin with vectors in the plane. Now let me begin by reminding you of something that you probably already know, and that's that some natural quantities are scalars and other natural quantities are vectors. So let's take a look at scalar quantities first. A scalar quantity has a magnitude but no direction. So a good example of this is pressure. Pressure is a scalar quantity. On the other hand, some natural quantities are vector quantities, and a vector quantity has both a magnitude and a direction. So a good example of this is wind. Wind is a vector quantity. You want to know not only how many miles per hour is the wind blowing, but you also want to know in what direction is the wind blowing. So it's natural to think of wind as a vector quantity having a magnitude and a direction, whereas pressure is merely a scalar quantity. So we can see in nature this distinction between quantities that are scalars and quantities that are vectors. On the other hand, we don't want to think that these quantities never interact in a meaningful way with each other. And here's a simple example. We've got interactions between pressure and wind in the weather. So here's a map of the United States. The pressure is being given to us in kind of a topographical way. We can see that these lines here are lines of constant pressure. So every point along this line has the same pressure. And we can see that as we move across this part of North America here, that the pressure is dropping as I move from one of these contour lines to another. Now the wind is being given to us just by the green arrows. So the green arrows are trying to tell us both the speed of the wind and the direction of the wind. And it's interesting just to look at this very casually and notice that these regions of high pressure, what we typically see is the wind is trying to exit these regions of high pressure and move to regions of lower pressure. An attempt to equalize the pressure is in some sense creating the wind. So we can see beautiful interactions here between a scalar quantity, in this case the pressure, and a vector quantity, in this case the wind. Now let's take a look, because this is going to help us as we move forward in this discussion. Let's take a little closer look at these wind vectors, because we're going to want to study vector quantities. So here's a close-up view of wind vectors. The black arrows in this picture represent wind vectors. They show the direction and intensity of the wind at the location given by the tail of the arrow. So the longer the arrows, the stronger the winds. Now, in building a mathematical model for vectors, we can take a cue from this picture. What is it that we need to do in order to specify one of these arrows? Well, we have to specify the tail of the arrow, and we also have to specify the head of the arrow or the tip of the arrow. So in other words, this arrow is being determined by 2 different points in the plane. So given 2 points in the plane, A and B, we can talk about the arrow from A to B, or the vector from A to B, or the directed segment from A to B. And the notation we're going to use is we'll write A first, B second to mean that the arrow is directed from A to B, or the vector is directed from A to B. And so we'll say A first, B second with the arrow over the top is referring to this vector, the one that starts at A and ends at B. And the points A and B are called the tail and the head of the vector AB respectively. Now, amongst all the vectors in the plane, we want to give prominence to a certain class of vectors called position vectors. So a position vector in the plane is a vector whose tail is at the origin O. In other words, a position vector is a vector of the form O to A, or O to B, or O to C. So in other words, any point in the plane can serve as the head of the arrow, and the base of the position vector will always be the origin. So an important thing to take away from this discussion is that there's a natural correspondence between position vectors and points in the plane. So if I hand you a point in the plane, say A, this gives rise to the position vector that goes from O to A. On the other hand, if I give you the position vector, you can see where the tip of that arrow is, or you can see where the head of that arrow is, and that will give you the point in the plane that the arrow is pointing to. So again, there's a natural correspondence between position vectors and points in the plane. Now remember, a point in the plane is specified by a pair of coordinates, an x and a y coordinate. And so we're going to make use of that to help us discuss what are called the components of the corresponding position vector. Since points in the plane are in perfect correspondence with position vectors, we can think of the position vector from O to A as given by or represented by the coordinates of the point A. Now, there can be a lot of confusion then between, are we talking about the point A or are we talking about the position vector from O to A? So in order to allay some of this confusion, we're going to use the following notation or nomenclature. All right, so for instance, suppose we're talking about the point with x coordinate 3 and y coordinate 2. When we're talking about the point 3, 2, we're going to use these open parentheses. This is the usual convention for designating a point in the plane. And we're going to talk about the two parts, 3 and 2, as the coordinates of that point. So we'll use the open parentheses and the term coordinates to refer to the 3 and 2, respectively. Now, when we're talking about the position vector that starts at the origin and terminates at 3, 2, we're going to use these squared off brackets. So the squared off brackets will remind us that this is the position vector that terminates at the point 3, 2. And rather than call the 3 and the 2 the coordinates, we're going to call those the components of the vector. So we have notation for points and we have notation for vectors. We have nomenclature. We talk about coordinates of a point, and we're going to talk about the components of a vector. But remember that every point in the plane does give rise to a position vector, and every position vector does give rise to a point in the plane. There is this natural correspondence between them, but they truly are different things, all right? And we want to make sure that we keep that distinction straight in our minds. Now we're going to talk about row and column vectors, and this distinction is not going to be a big distinction for us now. It's really just a matter of convenience in terms of representing a vector. So this will matter much more later, but for now let's note that a vector can be represented as a row of components or as a column of components. So as far as we're concerned at this point in the course, we're not making a distinction between the vector with components 5 and negative 16 represented as a row, or the same vector with components 5 and negative 16 represented as a column. So we will have different names for these objects. So the first one is going to be called a row vector, and this second object will be called a column vector. Let's talk a little bit about some common notation and some common concepts. So the 0 vector is the position vector with components 0 and 0. In other words, the tail and the tip correspond to exactly the same point, namely the origin. So that's going to be our 0 vector. We're going to say that two position vectors are equal if they're equal component-wise. In other words, component by component, as we work our way from left to right, component by component, they are the same. Often vectors will be denoted by a single lowercase letter in bold font. So when we talk about a vector quantity, we're typically going to notate that with a boldface lowercase letter. So for example, we can talk about the vector A having components negative 13 and 28. Now, these symbols cannot be written easily by hand. So when there is any possibility of confusion, we will use an arrow to designate a vector quantity. So you may have to write your vector A as A with an arrow over the top, but you might see it in print as a bold-faced lowercase letter A in a typed font. Okay, the set of all position vectors in the plane is denoted by this symbol, uppercase R with a superscript 2. Now that's called a blackboard bold font, so it's a blackboard bold font R with an uppercase 2 or a superscript 2, and that's going to be our symbol for the set of position vectors in the plane. Now let's talk about the components of non-positional vectors. So let's say the wind at A is given by the vector AB. The components of AB are always given or measured relative to the position A. For example, let's suppose that the base of our arrow is at the point 6, 3, and that the tip of our arrow or the tip of our vector is at the point 11, 12. When we talk about the components of the vector AB, we're always measuring this relative to the position A. So relative to A, the components of this vector are going to be 5 to the right and 9 up. So we would say the components of the vector AB are 5, 9. Now, what's important to realize is I can take those components 5 and 9 and I can generate a point in the plane with those coordinates, and let's call that point P. So P has coordinates 5, 9. This generates a positional vector that of course starts at the origin and ends at the point 5, 9. And what we'll notice is that this positional vector has exactly the same components as the original vector from A to B. This, of course, is now a positional vector. Its base is at the origin. So the vector OP is what's called the standard position for the vector A to B. So what is the standard position? It's a positional vector whose components are identical with the original vector. Geometrically, you can just think of it as taking this red vector from A to B and translating it in the plane until the base of the arrow sits at the origin. And that's what's called the standard position vector for AB. Now let's talk about equality of non-positional vectors. So let AB and CD be vectors. We see that AB is equal to CD if they have the same components. So AB is equal to CD if they have the same components. Now, that is absolutely equivalent to saying that if I were to take the vector from A to B and put it into standard position, and if I took the vector from C to D and put it into standard position, they would coincide with each other in standard position. So having exactly the same components is equivalent to saying that they have exactly the same standard position. Now, what would this mean physically? So let's suppose that AB and CD represent wind vectors. What this is saying is that a person that's situated at A is having exactly the same experience with the wind as a person that's sitting at position C. So this is what we mean by the equality of vectors when they are not in standard position. Our next subsection is called New Vectors from Old, and in this section we will begin to explore some of the algebraic qualities of vectors. So we'll learn how to add vectors, how to subtract vectors, how to scale vectors, and we'll discover some of the underlying geometric consequences of vector addition, vector subtraction, and scaling. Let's begin with vector addition. Let U be a vector with components A and B, and let V be a vector with components C and D. I want to form a new vector called U plus V, and the rule is actually pretty simple. It's just add component-wise. So grab the first components, A and C, and add them together. Grab the second components, B and D, and add them together, and you get the first and second components of the sum U plus V. So it's actually quite simple. So vector addition is quite simple. Now, I do want to caution you here because there's a little bit more going on here than meets the eye at first. Everything I've described to you is true, but it's a little more fussy than what it appears at first blush. So let's fine-tune this a little bit. I'm actually forming the sum U plus V, and I want you to take note that U is on the left and V is on the right. So I'm forming U plus V. And according to this definition, I actually have to add within the components in exactly that same order. So I have to use A first and C second, A plus C, and B first and D second, B plus D. So if we look at this, it's a little fussier than it might appear at first. So if I want to form U plus V, I have to make sure to add the components in exactly that same order. That's how I find the sum of u plus v. Now, if you're a sensitive soul, you may be already wondering if you get a different result if I add the vectors in the order v plus u. So let's find out. So suppose I want to form the vector sum v plus u. What do? I get the first component of v, I get the first component of u, and I add them together in that order. So I'm going to have c plus a. Then I do the same thing with the second components. I take d and I take b and I add them together in that order. And the question is, are these the same vector? Is the vector u plus v the same as the vector v plus u? Well, let's remind ourselves, how do we test equality of vectors? How would I know if a pair of vectors are equal to each other? Well, the rule is two vectors are equal if and only if they are equal component-wise, component by component. And so the question boils down to, is a plus c the same as c plus a? And the answer is yes, because addition is commutative under the ordinary rules of arithmetic on the real numbers. So a plus c and c plus a are the same thing. B plus d and d plus b, again, because addition is commutative on the real numbers in the ordinary sense, those components are also equal to each other. So since these are equal component-wise, these vectors, in fact, are equal to each other. So one thing we get from this is we know that vector addition has a fairly simple rule, add component-wise, and in fact, vector addition is commutative. It doesn't matter if I add the vectors in the order u plus v or v plus u, I get the same resulting vector. So vector addition is in fact a commutative operation. Of course, this defines vector addition in purely algebraic terms, and what we'll see is that there's a very simple and beautiful interpretation of vector addition on geometric terms or on geometric grounds. So another way of thinking of vector addition is to begin with the vectors u and v here in standard position, and if I want to find, for instance, the resultant vector u plus v, I simply grab the vector v and I translate it until the tail of v is at the tip of u, and then I find the tip of that resultant vector, and the positional vector I get by starting at the origin and going to the tip of that translated v gives me the resultant u plus v. So that's as if I go u first, v second. Now we know that vector addition is commutative, and this is reflected geometrically by going v first and then u second. And we see that these tips coincide no matter the order in which we would add the vectors. So if I go u first, v second, or v first, u second, I end up at exactly the same point, and so I end up with exactly the same resultant vector, whether I think of it as u plus v or v plus u. And so one thing we want to notice, though, is that this always outlines for us a parallelogram, right? This is always going to give us a parallelogram in two-dimensional space where we have the sides are determined by the vectors u and v, and one of the main diagonals is described in terms of the sum of u and v. Our next main operation is called scalar multiplication. So let u be the vector with components a and b, and let c be a real number. And in this context, it's always called a scalar. And I want to form a new vector called c times u, right? A product of a scalar quantity and a vector quantity. So this is going to give me a vector, and it's easy to describe what that vector is. I simply take the components of u and I magnify them or multiply them by that scalar c. So the result of this is what's called a scalar multiple of u. Now let's look at the effects of scalar multiplication. So let's picture an original vector u here in blue, and I want to think first about what happens when I multiply by the scalar 2. So I want to form a new vector called 2 times u. And the effect is going to be to take each component of u and multiply it by 2. And so the effect is going to be that this new vector will point in exactly the same direction as u, but it will now be twice as long. Now let's think about the effect of multiplying by negative 1/2. So let's look at the vector negative 1/2 times u. Well, by virtue of multiplying by a negative number, we are actually going to be changing the direction of u. The new vector minus 1/2 times u will be pointing in the opposite direction. And because we're multiplying by a number in absolute value, which is less than 1, we'll actually be shrinking the length of the vector. The vector will now be 1/2 as long as the original vector. So you can see the various results of scalar multiplication. You can magnify or shrink the vector, you can preserve the direction, or you can invert the direction. So these are all the manifold effects of scalar multiplication. But in all cases, multiplying by a scalar will produce another vector that's collinear with the original vector. The language of scalar multiplication allows us to carefully define what it means for a pair of vectors to be parallel. So, the vectors AB and CD are parallel, provided that their vectors in standard position are scalar multiples. In other words, if I wanted to show that this vector AB was parallel to this vector CD, the first thing I would do is I would write the vectors in standard position, and then I would show that either I can get from the red to the blue by scaling, or I can get from this blue vector to the red vector by scaling. But that's what would be required to show that the vectors, in fact, are parallel to each other. Now, to put this idea to the test, let's work the following problem together. So, let A have coordinates 5 and 3, B have coordinates 9 and 8, C have coordinates 2 and 11, and D have coordinates -8 and -1. Are the vectors AB and CD parallel? Well, let's work this problem together under the document camera, so I'll meet you over there for the solution to this problem. All right, so welcome to the document camera. Let's work this one together. The first thing I'm going to do, and this is not absolutely necessary, but I want to plot these points and draw the vectors just to get a sense of how these vectors are related to each other geometrically. And then we'll work through the rest of the problem. So let's plot these points. So A is situated at 5, 3. It doesn't have to be perfect. I'm going to put it roughly there. B is situated at 2, B is situated at 9, 8. We're going to put C at 2, 11. This is close enough for what we're trying to get out of this. And then D is going to be at -8, -1. -8, -1 will be roughly in this vicinity. Okay, so the vectors we're looking at, there's one vector that goes from A to B. And then there's another vector that goes from C to D. Now, we haven't drawn this picture perfectly, but it's pretty close. We don't know if these vectors are parallel or not, but it's suggestive that they might be parallel to each other. Now, in order to work out the details, we have to appeal to the definition of parallel. And what do we have to do? We have to find the components of AB. We have to find the components of CD. And then we have to see if there's any way to scale one of these vectors into the other. Can we find a scalar such that multiplying one vector by a scalar will turn it into the other vector? So let's work out the components for AB and for CD. So an easy way to do this is just to write the coordinates on top of each other. So we'll put the 9, 8 above the 5, 3. And then just do some coordinate-wise subtraction. So 9 minus 5 is 4, and 8 minus 3 is 5. So those are the components of the vector from A to B. And then we'll do the same thing here. Now we have a vector that's going from C to D, so we have to make sure we do the subtractions in the right order. So we'll have -8, -1, 2, 11. So -8 minus 2 will be a first component of -10. -1 minus 11, a second component of -12. All right, and so that's the components of the vector from C to D. And now the question is, can I scale, for instance, can I scale this one to this one? So can I find a number C such that C times 4, 5 brings me to -12, -10, -12? Can I multiply this vector by a scalar that brings me to this vector? Now, what does it mean to scale this vector by c? That means I get 4 times c and 5 times c. So equivalently, can I do this? Can I find a c such that this vector is equal to this vector? But what does it mean to say that two vectors are equal to each other? It means that the first components are equal and the second components are equal. So this is equivalent to saying, can I set 4c equal to negative 10 and simultaneously 5c equal to negative 12? Can I find such a c? So we have to look for simultaneous solutions, right? We're looking for simultaneous solutions to 4c equals negative 10 and 5c equals negative 12. Can I find a single number c that does both of these things? Well, let's take a look at the second equation. That's saying that 5c is equal to negative 12, and so that tells me that c must be equal to negative 2.4. So if that c is going to work in both of these equations, I should be able to plug negative 2.4 in here for c, and I should get negative 10. In other words, everything now hinges on whether when I plug in negative 2.4, I get negative 10 or not. All right, so let's plug it in. So I'm going to take 4 times negative 2.4. When you work this out, you're going to get negative 9.6, and that is not equal to negative 10. It's close, but it doesn't work. And so what that's telling me is that there is no single number c that can satisfy both of these equations simultaneously. So I cannot find the number c that scales this vector into that vector. And so this tells me that the vector AB and the vector CD are not parallel. And that's all we have to show, that there's no way to scale one into the other. So that is our solution to this problem. So join me back at the class notes. We'll look at some more stuff. So our next topic is vector subtraction. So let U be a vector with components A and B, and let V be a vector with components C and D. The vector U minus V is what I get by simply subtracting the components in the natural order. So if it's U minus V, I will subtract the components in the order U minus V. And this is what we would call the difference between U and V. And I want you to notice that in general, U minus V and V minus U are not going to be the same thing because there's an order imposed on the subtraction of the components. So in general, we would not expect U minus V and V minus U to be the same vector. Now, let's work a problem together where we explore this concept a little bit. So I want to let U and V be vectors in the plane, and I want to show that V plus parentheses U minus V, so the vector U minus V, those vectors add up to the vector U. So V plus quantity U minus V always equals the vector U. And then I want to use this to create a geometric interpretation of vector subtraction. So join me over at the document camera. We'll work on this one together over there. All right, welcome to the document camera. Let's work through this problem. In problem 1, we're supposed to show that V plus the quantity U minus V is equal to U, where U and V are just some vectors in the plane. And a simple way to do this is just to do it using some components, right? So let's imagine that the vector U, and I'll use arrows here because it's going to be hard to write this as a bold font. So I'll just say let the vector U have components, let's say A and B. And let's say the vector V has components C and D. Now the first thing we're going to want to work out is this expression in the parentheses, because when we parse this left-hand side, we have to realize that we have to do this calculation first and get a single vector to represent U minus V. And so when we do that, when we take U minus V, we just have to do the subtraction component-wise in the proper order. So U minus V suggests that I have to take the subtraction in this order. So I'll have A minus C in the first component and B minus D in the second component. And that gives us this vector U minus V. Now the second part of the calculation here is to add v to the result of that vector that we've just computed. So we're going to do the vector v plus the vector u minus v. And so that's going to be what I get when I take the vector cd and I tack on the results of the vector I just computed, namely a minus c, b minus d. And when I add two vectors, I simply have to add their first components and add their second components, and those become the two new components of the resultant. So I'm going to have c plus a minus c. And I'll have d plus b minus d. I'm showing this to you in all the gory details. You can skip some of these steps. But the net result is, in the first component, I'm going to have c plus a minus c. That's simply a. And I'll have d plus b minus d. That is simply b. And we recognize that the vector ab is none other than our old friend, the vector u. So if we think about this, beginning on this extreme left-hand side, we've shown this extreme left-hand side is equal to this extreme right-hand side. So we've fulfilled the requirements of this problem. We've shown that that's always true. Now, we want to use this identity that we've just constructed, use this to create a geometric interpretation of vector subtraction. So we have a nice geometric interpretation of vector addition. We're now going to use this to help us gain an understanding or a geometric interpretation of vector subtraction. Now to do that, let's first draw a pair of vectors u and v. So I'll call this one, let's say, u. And I'll call that one v. Now let's think about what this is saying. This is saying if I add u minus v onto v, I get u. So I have to think of a vector that I could add onto v to get to u. That would be a way of thinking about u minus v. It's the vector that I have to add onto v in order to get to u. And if we think about it that way, we can see it in this picture. If I draw a vector that starts at the tip of v and ends at the tip of u, that's going to be this vector u minus v. So a way to see vector subtraction is to imagine this vector. So we can think of u minus v. We can think of this as the vector that I can add on to v that gets me to u. So there's our image of vector subtraction. So if you had to write or draw the picture of the vector subtraction v minus u, what picture would you draw? So let me draw a scenario for you and see if you can intuit the right answer here. So if I draw a v here, and u there. The question is, how would I draw the picture v minus u? All right, so you might want to pause the video here and imagine what you would do. But imagine drawing now the picture of v minus u. Okay, so let's think about that. What does v minus u have to do? V minus u has to be the vector that would satisfy this. It would be the vector that I would add on to u that would get me to v. And so geometrically, it would have to be in this picture here. Okay, so there's two vector representations, one for u minus v and another one for v minus u. And that's based on the same pair of vectors. I'm just taking the subtractions in the two different orders. All right, so hopefully that helps you understand what vector subtraction is about and how we can visualize it given the vectors u and v. I want to share one last idea with you concerning vector subtraction. And this is a nice idea because it allows us to take vector subtraction and think about it in terms of vector addition. And here's the idea. So let u and v be vectors in the plane. And for the sake of argument, let's say that u has components a and b, and that v has components c and d. Now, to get started thinking about this calculation, let's imagine we were trying to calculate the following vector sum. I want to take u and I want to add to it -1 times v. So what is that going to look like in terms of the components? I'll have ab plus the scalar -1 times cd. So let's do the scalar multiplication first. When I multiply through by -1, I'll have new components, -c and -d. Now I'm going to do the vector addition. So we take the first components and we add them together, and then we take the second components and we add them together. So the result is going to be a first component of a minus c and a second component of b minus d. But if we sit back and stare at that, those are exactly the components of the vector u minus v. So in other words, what we've discovered is that I can write u minus v as a sum, as a vector sum. In this case, u plus -1 times v. Vector subtraction can be written in terms of vector addition as long as I'm willing to scale one of the vectors by -1. And this is, in fact, a helpful idea from time to time. This next subsection is entitled Vectors in R3 and Rn, in other words, three-dimensional Euclidean space, and in general, n-dimensional Euclidean space. And what we'll find is that all of our notions that we've developed in two-dimensional space will have natural analogs in three and in general n-dimensional space. So in particular, vector addition and scalar multiplication will look exactly the same. They'll have natural analogs. Now, what we lose as we move up into higher dimensions is the ability to picture things geometrically. So as we make this move out of 2 dimensions into higher dimensions, let's think first about 3-dimensional space, right? In R3, a position vector is specified by an ordered 3-tuple of real numbers, let's say a, b, and c. And so, for example, here is a picture of the vector a with components 1, 2, and 3. And we can easily imagine getting a picture of this vector by imagining moving one unit in the x direction, 2 units in the y direction, and then 3 units in the z direction. We locate that point with coordinates 1, 2, 3 in 3-dimensional space, and we can draw a picture of the vector that starts at the origin and ends at that point 1, 2, 3, and identify that as the vector A. So even in 3-dimensional space, we can still picture what these vectors look like. Now, we can continue to abstract the idea of a vector to higher dimensions even if we can no longer picture it. So in general, for n greater than or equal to 1, a vector in Rn is specified by an ordered n-tuple of real numbers. So the components, we'll just label them generically A1, A sub 2, on out to A sub n. So when we're in 4-dimensional space, we'll expect 4 components. When we're in 5-dimensional space, R5 will expect 5 components, etc., etc., etc. Now, we can no longer picture these things once we get into 4 and higher dimensions. Nonetheless, the concept of a vector in these higher dimensional spaces will continue to be extremely useful to us. So even if we can no longer picture these vectors geometrically once I get to dimensions 4 and above, the concept of a higher dimensional vector is still incredibly useful, especially if we think of each component of the vector A1, A2, up through AN as holding some small piece of the whole, storing a small piece of the whole. So that the entire vector represents a totality, and each component is contributing some small part to that whole. So for example, this happens all the time when we think about digitizing audio files. So think of this red curve as representing a pure sound wave. Well, we can take this red curve and we can sample it at a fixed frequency and store the results of those samples as components of a vector. So now this vector, in some sense, somewhat imperfectly, but in a way that we can't detect with our own ears, it stores that entire information of the red wave, and each component of that vector is just storing a slice, a bit of information along the way. Now, that vector can now be manipulated, right? We can talk about scaling that vector. We can talk about adding these kind of sound vectors together in ways that are still meaningful. So even though we can't picture what this would look like in space, it still carries a lot of meaning. So if we have this idea of higher dimensional vectors as a totality and each component adding a bit of information to the whole, that's a helpful picture going forward. Okay, now what I want to do is look at some algebraic properties of vectors in n-dimensional space, and we're going to look at we'll prove a couple of these things together on the document camera, but let's just look at some generic properties of vectors in n-dimensional space. Now, throughout this theorem, we're going to let u, v, and w be vectors in n-dimensional space, and c and d are going to be scalars. Now, this theorem has got parts a through h. I'm going to work out some details for proofs for parts a and b. We'll do that together at the document camera, and then you will work out parts C through H on your own. Now, my hope is that once you see how we work out the details for A and B, you'll have no problem imagining how to do parts C through H. So I'll leave those for you to do on your own. That'll be a good exercise for you. Now, let's take a look at each of these parts A through H in some detail and make some comments on each of them. So, part A, we've already saw this result in 2 dimensions, and it's saying that this is just true in general, that when I add vectors, u plus v, that is the same as adding them in the order v plus u. So that's the usual commutative law for addition, and it says vector addition satisfies the commutative law. Now, part B is the usual associative law, in this case for vector addition. And we just have to be a little careful in the meaning of the left-hand side and the right-hand side. So when we see these parentheses, that's basically directing us to make sure that we first add u and v together and then add w to that result. And on the right-hand side here, we're saying first we add v and w together and then add that to u. And what this is telling us is that no matter how we group these things, no matter how we would think of ordering this set of operations, we're going to get the same result no matter what. So whether we group them u plus v first and then add w, or group v and w together and then add u, no matter how we do that, we're going to get the same result. And basically that gives us some liberty. It says, if I were to see the string of vectors being added together, u plus v plus w, I would have no problem in interpreting the answer, right? Because it says I could think of adding u and v together first and then bringing in w, or adding v and w together and then bringing in u. No matter what, we're going to get the same result. Now, part C is really just a special property of the zero vector, so the vector that consists entirely of zero components. It says if I were to take a vector u and add the zero vector to that, not surprisingly, I just get back the vector u that I started with. So that's really a property of the zero vector. Property D is a property of what's called an additive inverse. So if I take the vector negative u, so the vector I obtained by negating all of the components of the original vector, and I add that on to the vector u, I just get the zero vector. And so this is what's called an additive inverse. It says the vector negative u is acting as an additive inverse for the vector u. Okay, now parts E and F together are giving us what are usually called distributive properties, but they are different, right? So the first one, property E, says that scalar multiplication distributes over vector addition, right? So the addition here is vector addition and the multiplication is scalar multiplication. So in this case, I have C times the vector u plus v is the same as C times u plus C times v. So the scaling distributes over the vector addition. Now, in property F here, the addition is the addition of the scalars, and then we're multiplying that by the vector u. So in this case, we can almost think of the vector as distributing across that sum of scalars. And so when I see C plus D times u, I can think of that as C times u plus d times u. That's what's occurring here on the right-hand side. Now, in truth, if we're using property f, we're almost always using it in this direction. For instance, I might see 2 times u plus 3 times u, and I immediately can write that as 5 times u. So in this direction, we would normally call that factoring, but that's typically the utility of property f. It just says I can quickly see something like 5 times u plus 8 times u and recognize that that's the same thing as 13 times u. So property f is going to be used almost unconsciously all the time and most often in this direction, kind of simplifying things by factoring out these scalars. Property g is really just about what happens when we take successive scalings in a row. So for example, it says, suppose I take a vector u and I scale it first by a factor of 2 and then again by a factor of 3. What property g is saying is I can think of that as a single scaling by a factor of 6. So I can take kind of successive scalings and treat that as one single scaling. So scaling by a factor of 3 and then by a factor of 4 is the same as scaling by a factor of 12. And finally, property h is a simple property, but it's identifying the scalar 1 as special. It says anytime I take a vector u and I scale it by a factor of 1, that leaves the vector u unchanged. So it says amongst all the scalars, the scalar 1 has the special property of leaving the result unchanged. So scaling by anything other than 1 is going to change the vector, but scaling by 1 leaves the vector unchanged. So what I want to do is go to the document camera and we'll work out some detailed proofs for parts A and B just so you can kind of see how that works out. And then I'll leave you to kind of work through parts C through H on your own. So join me at the document camera for the proofs of parts A and B. All right, so welcome to the document camera. Let's work through properties A and B here, or parts A and B of this theorem 1.1. So this is the all-important commutative law for addition and the associative law for addition. Now, this is going to be true for vectors in Rn. I think the proof will be just as well done. Let's just do this in R4, for example. Let me show you what the proof would look like in R4, and you can use your imagination to see what the proof would look like in any dimension. It really doesn't depend on the dimension that we're working at. Okay, working in. All right, now to do this, to do both of these parts A and B, we're going to need up to 3 different vectors. So let's just bring some vectors to life here. We're going to have a vector u, and its components are going to be u1, u2, u3, and u4. We'll have a vector v with components v1, v2, v3, and v4. And then we'll have a vector w. We won't need w at first because we just need to work with u and v in this first one, but we'll bring that in part B. We'll have it ready for us here. Okay, so we've got u, v, and w, and all of these are members of the 4-dimensional Euclidean space R4. So let's do this commutative law, and we're just going to do the kind of tried and true strategy where we, let's say, start on the left-hand side and manipulate it until we end up on the right-hand side. All right, we could just as well start on the right-hand side and do some manipulations until we get to the left-hand side, and it doesn't really matter in this case. We'll start on the left and work our way to the right. So what we want to do is we want to start with start by writing out the vector u plus v, and we'll do some work on that until we culminate in something that looks like v plus u. So what does u plus v look like? Let's start here. Well, according to our definition, we should add component-wise in exactly the same order in which these appear. So we should take the components of u and add the components of v component-wise here. So we'll have u1 plus v1, u2 plus v2, u3 plus v3, and finally u4 plus v4. That's according to the definition of vector addition. And now what we're going to do is use the fact that within each of these components, these are just sums of real numbers. This is just ordinary arithmetic of real numbers. And we know that in ordinary arithmetic of real numbers, we can freely commute the members in addition. So this is the same thing as v1 plus u1, v2 plus u2, v3 plus u3, and v4 plus u4. So again, that is just resting on the fact that I can commute under the normal rules of arithmetic of real numbers. Now, if I stare at this, I've now got the components of v first and the components of u second. And so this is the same thing as v plus u. All right, and so we have achieved part A. We've got our proof of the commutative law. So I will close that off with a little black box. The proof is over. So that's our proof of A. Now what about the proof of B? Again, we'll just bring in our vector W here to help us in this one, but we'll start on, let's say, the left-hand side and work our way to the right-hand side. So the first thing we have to do is we have to form the vector u plus v, and then we have to add on to it the vector w. Well, we've already got u plus v sitting here, and so we just have to tack on or add on the vector w to this vector u plus v. So our vector u plus v, parentheses, plus w will look like u1 plus v1 plus w1, u2 plus v2 plus w2, u3 plus v3 plus w3, and then finally u4 plus v4 plus w4. Okay, so I kind of ran out of room here, but you can kind of just chain these things along. Now what does that equal to? Well, by the associative law of arithmetic for real numbers, I can take these parentheses off u1 plus v1 and associate them, wrap them around v1 plus w1. So just in this first component, using the associative law for arithmetic, I can rewrite this as u1 plus v1 plus w1. Then I can rewrite this one as u2 plus v2 plus w2, u3 plus v3 plus w3, and then finally u4 plus v4 plus w4. Okay, so this would be a good time to just take stock of what we've done. All right, let's think about this again. We started here with u plus v plus w with parentheses on u plus v. So we added those vectors together just using the method for adding vectors in Euclidean space. All right, we add component-wise. Now here was the crucial part in the proof though, right? We said in each component now, apply the associative law of arithmetic. So we can lift these parentheses off of u1 plus v1 and put them on v1 plus w1. And then I can do the same act in every one of these components. So component-wise, I can make these changes, right? I'm using 4 applications of the associative law, if you will. Now, I basically have to go through the process of ripping this apart now. I have to recognize that this can be ripped apart and written as u1, u1, u2, u3, u4 plus v1 plus w1, v2 plus w2, v3 plus w3, and v4 plus w4. I can keep the parentheses on here. Doesn't matter, but I'll put them on there just for the visual, right? So this is just the process of ripping these things apart component by component and realizing that I can recognize this as a vector addition, as a result of a vector addition. So in other words, if you wanted to convince yourself that this last step was true, I could recombine first components, recombine second components, recombine the third components, and recombine these fourth components. All right, so this is a process of recognizing that this is just a vector sum. And then I can realize that this too is a vector sum. This is a vector sum of v plus w. So at the end of the day, what do we have here? We've got the vector u being added on to the vector v plus the vector w. Okay? And that's exactly what we wanted to show. We wanted to show that u plus v plus w is equal to u plus v plus w. That's exactly what the associative law is. And if you remember, the crucial step here was the step from here to here where we applied the associative law of arithmetic in each and every component. We did 4 applications of the associative law for arithmetic, and that was the crucial thing that allowed us to crack this open. So we have now available to us this associative law for vector addition, which is very, very handy and useful and important. Okay, I'll let you try to work out parts C through H on your own. You can model them on what we've done here. I think you'll find them to be fairly tractable for you. So give those a try. I would encourage you to do that. Let's go back to the class notes. Now I want to work a problem with you where we put some of our theory into practice. And what we're going to do in this problem is we're going to first simplify an expression, and then we're going to solve an equation. And what I want us to concentrate on when we're working both parts, parts 1 and 2, is how we're using the theory that we've developed in Theorem 1.1, how we're using that in each and every step of the process. So every step of this process is being justified in some sense by one of the parts A through H in Theorem 1.1. So let's go to the document camera and work problems 1 and 2 out in some detail with the intention of seeing how Theorem 1.1 gets put into practice. All right, welcome to the document camera. Let's work these problems together. And the first thing we're going to do is we're going to think of u, v, and x as some vectors in the plane, or in Rn in general. And what we want to do is take an expression like this and use our results from Theorem 1.1 to try to help us simplify this expression, break it down into something much easier. All right, and let's try to be, at this point in the course, let's try to be very conscientious about what parts of Theorem 1.1 we're using in each step. Now, when I see something like this, I'm primarily seeing the sum of 3 vectors, and we know from the associative law that we don't really need some parentheses to tell us the order in which we're going to add these vectors together, because it really doesn't matter in the end. But the first thing I want to do is I want to take this middle expression and I want to use the distributive law and break this into a sum of 2 vectors. And in doing this, I'm going to have to distribute the 5 onto the 3u and onto the 4v. So let's take a look at that. So this will be equal to 7u. I'll keep the parentheses here at this point. I'll have 5 times 3u and 5 times 4v. And then I'll be adding on 8v. Still working inside these parentheses. Remember my double scaling law? We called that was property G. If I'm scaling a scalar, right, that's the same thing as just doing 5 times 3 or 15 times u. And again, the double scalar law, if I'm doing 5 times 4v, that's the same as 5 times 4 times v. So that's simply 20v. Okay, and now the associative law comes to the rescue again, and it just says if you're just adding up a bunch of vectors, it doesn't matter where you put the parentheses. You can pull the parentheses off and reassociate things. So this will be 7u, 15u, 20v, and 8v. And if I want to, I can put the parentheses back down here and here just to indicate that these 2 expressions only involve the vector u, and these 2 expressions only involve the vector v. And then finally, I can use my distributive law kind of in the reverse form, more like factoring law, but it's the distributive law that allows me to write this first expression as 7 plus 15 times u and 20 plus 8 times v. In other words, 22u and 28v. And that's what I would call a simplified expression of that original expression. Okay, I've taken something that was as involved as this and I've broken it down into a simple combination of u and v, 22 times u and 28 times v. So that's the end of part 1. Simplifying an expression, a very important task. It's nice to be able to do that and to be able to do it quickly and confidently. Now I want to solve for x in this equation. All right, now what I'm going to do first is to work on this left-hand side. Most of my work initially is going to be over here on this left-hand side. And the first thing I want to do is, this is really a difference between two vectors. This is a vector subtraction, and I want to use my idea that I can always write a vector subtraction as a vector addition. So just on this left-hand side, I can always write this as 8x plus a negative 2 times u plus x. And that's going to be equal to 7u plus x. Okay. In my next step, I'm going to use the distributive law to distribute that negative 2 across. So this says 8x plus a negative 2 times u plus a negative 2 times x is equal to 7u plus x. All right. Now what I want to do, just as I would in an ordinary linear equation involving just a single variable, I'm going to try to isolate. I'm going to try to get x on one side, get the unknown on one side, and all the known things on the other side. So I'm going to try to bring this x from this side to this side. Now the way we can technically do that here in vector math is I have to think of adding some vector to this side that'll cancel out that x. And that vector is -1 times x. Or negative x, if you will. It's the same thing according to property D. But let me add -1 times x to this side and -1 times x to this side. Okay? Now before I do that, I just noticed something. I've got the 8x and the -2x. So let me first simplify this by bringing these two together as 8 minus 2 times x, or 6x. Okay, now let me add -1 times x to this side and -1 times x to this side. Okay, now what do we know? We know when I add x and -1 times x, that's the same thing as 0 times x. This is just the 0 vector. So this eliminates x from this side. So this side is just 7u plus the 0 vector, which is equivalent to or equal to 7 times u. Now what do we have on this side? I can bring the 6x together with the -1 times x as 6 plus -1 times x. So this is just 5x on this side. And I still have the -2 times u on this side. Okay? Now, anytime I add the 0 vector to anything, right? This is property C. Anytime I add the 0 vector to anything, I just get the thing itself. So this is just 7u on this right-hand side. So this equation can be written as 5x plus a -2 times u equals 7u. Now I need to add something to both sides of this equation that will allow me to get rid of this -2 times u that's on the left-hand side. And so I can simply add 2 times u to both sides. So I'll have 5x plus -2 times u plus 2 times u equals 7u plus 2 times u. Okay? Now when I use my distributive law, this was going to be -2 plus 2 times u. That's going to be 0 times u. So this is just going to be the 0 vector. When I use my distributive law again, this will be 7 plus 2 times u. This will be 9u.
Okay, so this now becomes 5x equals 9 times u. And then finally, I need to solve this just for x. I need to multiply both sides by a scalar that will reduce this down to just simply x. So I'm going to multiply both sides by 1/5. I'll scale both sides by 1/5. Now again, using my double scaling rule, this is the same thing as 1/5 times 5 or 1 times x. And this is going to be 1/5 times 9 or 9/5 of u. But 1 times x is just the vector x, and so this is simply x equals 9/5 u. Okay, so we've solved this equation. We've been able to express the vector x simply in terms of the vector u. Now, this is a lot of detail, and this is the kind of thing that I want us to think about here in section 1.1. Once we get very confident with what we're doing with in terms of this vector algebra, then we'll have no problem just taking an equation like this and very quickly getting to this answer. But early on, it's helpful to think about what's really motivating each and every one of these steps in solving this equation. As you can see, it's quite involved, and Theorem 1.1 is doing a lot of the heavy lifting for us. It's allowing us to make these kinds of calculations with some facility. So eventually we'll get to a point in the course where we're going to take an equation like this and just solve it almost reflexively, but at this point in the course, it's very helpful just to think about intentionally, how are we using Theorem 1.1 in each and every step of this solution?